Welcome back. Let's continue with our story of the Coarea formula. I repeated the theorem for a reminder. If you have a Lipschitz function from a larger Euclidean space into a smaller one, then you can integrate any compactly supported continuous function, say, for simplicity, on Rm by first integrating over fibers of the map F. Modulo this correcting factor, which is a kind of Jacobian, Cn dfx. And also the differentiability of f is given by Rademacher's theorem. As the first corollary, an important one, I want to deduce the integration in spherical coordinates from the Coarea formula. I kind of touched on this in the previous video, but the story wasn't complete. So let me show you why. The corollary will read as the following. If G on Rn is, we can do measurable, integrable, but again, for simplicity, we always want to say compactly supported continuous, then integrating G against the Lebesgue measure on Rn is the same as integrating over the ball of radius 0 r, G against the measure on the sphere, which agrees with the n-1 dimensional Hausdorff measure. We've talked about this agreement of measures in the area series. If you haven't checked that, please do so. And then r is a real value. For not negative r, the preimage is empty, so we could include the negative infinity as well. But this is not. So proof of this will be, let f from Rn into R1. So here this is our m and this is our n in the Coarea formula. B, the particular function which takes x to the absolute value of x. Then f is Lipschitz. So the coarea applies. And we have the derivative of f. So you may need some calculus here, but the derivative of at x is equal to the vector x divided by x. F is real valued, so its derivative is really just the nabla of f. It's a vector, and it happens to be this one for every x other than 0. At 0, it is not differentiable, but it's only 1 point, and remember, this is measure theory. In particular, the coarea factor, which here will be the one-dimensional one, of derivative of f at x, which by definition is determinant of derivative times its transpose, and then root will be just 1 for every x other than 0. This is a vector. If you multiply by its transpose, you get the length of the vector to the power 2. You take the root and you get back just the absolute value of the vector. And here absolute value of x cancels out the 1 in the denominator, you get 1. So that's the end of the proofs. Just plug everything into the Coarea formula and you get this. So, but this is not exactly what we call the integration in spherical coordinates. where is this factor r to power n minus 1? Where are the angles? To get that version from this one, the bridge there is that we can notice that all okay, I've messed up with the notation. B here is really just the sphere, not the disk, so just the boundary of the ball. So note that all spheres at radius r are scaled copies of the sphere at radius 1. In the R2 case, so this will be sphere of radius 1, and every other sphere you take is just a scaled copy of that. And because if you are in n-1 dimension, this is an n-1 dimensional manifold, so scaling multiplies in every direction the length by r. Therefore, the measure on let's say the measure dh1 scales by a factor of r to power n minus 1. So I'm relying on your familiarity with a little bit of manifold things. This is all rotation invariant, so nice and homogeneous. So you can justify it by using Riemannian metric, for example. The other way of justifying this will be that if you take a function with phi, which goes from the sphere of radius 1 to the sphere of radius r by just taking a vector x to the vector r times x, then we can use a change of variables for integration. Ultimately, that's the precise reason why the integration formula I'm going to write holds is because of the area formula, but this is a very simple version of that. The end, to cut the long story short, is that to integrate the function g over a sphere of radius r, we can pull back the values of g to the sphere of radius 1. So g is given along this sphere initially, but we can pull back the values to that. So this will be gr x, x being from the unit sphere, and then the scaling of the hn-1 measure gives this much. So here r to power n-1 is the area factor of the function phi, or rather its derivative. Okay. Therefore, if you have a parameterization, so the version of the integration in spherical coordinates follows. Because what we've shown so far is that g integral over r n dln is integral from 0 to infinity of s n. So this will be sphere of radius r g dh n-1 dl1 of r. This is what we have above. And now we instead of integrating over SR, each time we wish to integrate over the same sphere of radius 1 by the formula we had. So this will be Rx, R to power n minus 1, dHn minus 1, dl 1r, which you may be more familiar as just dr. If I want to really put it in the most familiar shape for you, the integration over S1 is you will take some angles that parameterize S1. So in 3 dimensions, this will be theta and this phi angle. So in 2, for example, in 3D, for example, that means spheres of dimension 2. This you parameterize S1 by 2 parameters, theta going from 0 to 2 pi, and then phi going from 0 to pi. And then you do g of Rx vector, and this becomes R to power 2 d phi d theta, and then this becomes dr. So that R2, that justifies where it's coming from. And x is written, can be written in the spherical coordinates just by the equations we have for it. What is interesting here, and this beautifully illustrates it, is that this factor that comes in has to do with the integration along the spheres, and has to do with this how these angles capture the measure on the spheres rather than with the R itself. So the right the only right way from this point of view to write integration, when you have R2, we call it more often polar coordinates. In polar terminology in math is messed up. Coordinates is that to integrate something on R2, you can do from 0 to infinity, from 0 to 2 pi. So in this case, there's only one angle needed to parameterize the sphere, and that is just theta running from 0 to 2 pi. And then you do g r r basically r theta. So this will be, yes, the point at angle theta and radius r. So I'm now forgetting my calc 1. So r cosine theta, r sine theta. So this whole thing is my Rx from above. And this, okay, so now the measure on the circle is r d theta, and then comes dr. So this is the right order in which that should be understood. That r d theta is the measure, this is dh1 on the circle of radius r. But of course, Fubini allows you to reorder them, and sometimes you see r dr d theta, for example. Depending on which integral is easier to calculate, we of course use both. But anyway, this is using some heavy machinery to get at the formula that we have been using already many times. Okay, that ends our first special example when Coarea formula applies and gives us interesting stuff. Fubini is not really an application of Coarea, because to prove the Coarea formula, you need the Fubini's theorem. And Fubini's theorem, in fact, is something more in measure theory than in calculus and analysis, because it actually works for product measure of sigma finite measures, and that's a whole different story. Okay. Next application is again to the case of f going from Rn into R1. So the target again is one-dimensional, is Lipschitz. Then, as before, for compactly supported continuous function g, integral on g on Rn of g against the Coarea factor. So the Coarea factor here will be so dfx will be a vector, just like before. Because it's a vector, multiplying it with its transpose, taking determinant and taking square root, just ends up giving the absolute value of that vector. If you like, let's put another one to emphasize it's not a number, rather the norm of a vector. So this dhn, which is just Lebesgue measure, is equal to integrating from negative infinity to infinity. So this is R1, the target space, and this is, you pick something in the target and then you look at the pre-image of f. So you can write like t. So you pick dt, you pick t from target space, and then this is the fiber over that. So first you integrate over n minus 1. Yes. So that is the formula, and just to be consistent, let me put L1 of t. Okay, there you go. So another integration formula for when f is mapped into R1. One thing that follows, so if this norm of d of x is positive almost everywhere, then we can just take g to be g divided by this value. G may lose being continuous, but it still is measurable. So we end up with the formula that integral of g dhn is equal to negative infinity to infinity of, so g is replaced by g divided by norm of dfx dhn minus 1 dl1 of t. So this is the set of points where f is t. And this gives a whole lot of examples already. So for example, one way of foliating R2 is by starting with y equal x squared and then shifting it up and down, just by adding a constant or subtracting a constant, like this. So R2 is foliated by these parabola. Can we integrate a function g on R2 by first integrating over these parabola? So this parabola will be y equal x squared plus c. So here I want to put t to be consistent with the previous notation. So you integrate g over that parabola, dh1, it's one-dimensional parabola. 2 minus 1 also is 1. And then you play around with this t. T negative infinity to infinity. Of course, we forgot to add this Coarea factor. So g df of x. But what is this df of x in this example? Here, f going from R2 into R, whose fibers are these parabola, is taking xy to the value y minus x squared. That's it. So f equal t is exactly this set here. So df of x, its gradient, is negative 2x and 1. If you recall from measure theory, this is perpendicular to the level set. So this is the derivative of f. In fact, it's pointing the opposite one direction, but doesn't matter because we're going to take its absolute value. So its norm, in fact, this is just a coincidence that it doesn't depend on y value. There's no other reason than just a coincidence. So this will be g, and this will be 1 plus 4x to power 2. So there you go. You have a, if ever your life depended on being able to integrate a function by first integrating over parabola, there is the formula for this. And another cool example that I couldn't resist putting here is the one where you wonder how you could integrate along diamonds and then sum them up to get the integral of a function over R2. So first we have to see what functions level sets will give this, and that function is just, you see that these are the boundaries of the L1 norm, but that is a fancy way of saying if you take f from R2 into R with f of xy equal to absolute value of x plus absolute value of y, then f is Lipschitz. Never forget to check that the assumptions of a theorem are actually satisfied. And what is the derivative of f of xy? Because of symmetry, I'm gonna just compute it for x positive and y positive. So for this quadrant, I can just drop the absolute values. So this will give me 1 and 1. Therefore, its norm happens to be independent of both x and y, and it's just constant root 2. Therefore, according to the formula above, to integrate a compactly supported continuous function, or just any non-negative measurable function for that matter, on R2, all I need to do is put 1 over root 2 here, run from, okay, so f is never actually negative, so I can start at 0, and then so this will be the diamond, but I don't have a name to say of radius this, of edge this, but it's just the set, the function g, dh1, and then dl1t. So up to this 1 over root 2 correcting factor, you can first integrate over this red diamond and then add them up as these shrink or expand to fill out R2. And to integrate over this diamond, you will ignore the 4 points remember the rectifiability thing, that will be actually an inevitable part of the Coarea formula, that the preimages are not C1 manifolds. They are C1 manifolds only up to null measure. You could even have uncountable many points with problems, but measure theory wins by ignoring them. And once you ignore those points, you know how to integrate over one edge, don't you? That had been the whole story with the area formulas that we did. But of course, even simple calculus tells you how to do this integral over that line. Okay, so that brings me to the end of some cool examples of the Coarea formula. I try to resist rushing to the full-fledged proof yet, because I believe seeing more examples adds to our motivation and justifies all the pain that we will go through to prove this amazing formula. But on the way also we will learn a lot of other things. So the whole goal is not just to prove this theorem. It is proven in books and in lecture notes. My goal is just to maybe add a little bit of perspective and context to it. So until next video, keep safe and please subscribe. I kind of feel that you have not yet. Thank you so much and have a wonderful day.